All right, so this is the last note section for this first part of Unit 4. So what we're going to talk about today is we're introducing this thing called dependent-independent events, where we're going to have something else going on. So for independent events, if we have two independent events, these are two things that do not influence each other. So they do not influence each other. So what happens is when one thing happens, it has no impact on the occurrence of another thing. So in this case, like in the last unit, what we said is, what is the case that we have that people like something sweet, and then what is the case that you have people who like something that's salty? So we take two different probabilities and we add them together. Well, this is a little bit different. This is two things that are completely independent, that have no impact on each other at all. So if I toss a coin twice, if I toss the coin the first time and I get a head, and I toss the coin the second time and I get a tail, there's no impact. Or if I have a boy and then I have another boy, or then I have a girl, it doesn't matter. So the results of something don't impact the other thing, and we call these independent events. And so when they're independent events, we take the two events and we multiply them together. So we would say if A and B, two different events, we would take the probability of A and the probability of B. So for example, here's how this would look. So I flip a coin and then roll a dice. So if I flip a coin, what is the probability that I flip a head? And then roll a 5. So remember, you have to write your probability statements. So probability that I flip a head and that I roll a 5. And what that would look like is the probability that I get a head times the probability that I roll a 5. Okay, so if I roll a head, it's 1 out of 2. I get a head out of 2 choices, head or tails. And then if I roll a 5, I get a 1 out of 6. So my probability here would be one option of 5 out of 6 options on the dice. So overall, I would have 1/12. And I'm not going to worry about putting that in the calculator right now just because I'm worried about time. All right? So what is the probability that Mrs. G will have 4 girls in a row? So probability of a girl and a girl and a girl. And so what happens is I have this probability that I have a girl 4 times in a row. So if I look at this, all of these probabilities are going to be the same. So if I have this probability of a girl, I have 1/2. But I have this 4 times in a row. I can write it as 1/2 times 1/2 times 1/2 times 1/2. Or I can write this as 1/2 to the 4th power, because it's the same thing 4 times. So this would be 1/8, which is 0.125. All right. I have a standard deck of cards. What is the probability that I pull a red card, replace it, super important, shuffle it, also important, and then pull a black card? Okay, so to get independence, you have to have replacement. If you don't have replacement, it changes your sample set or your sample space. If your sample space changes, then one thing affected the other thing. So we have to show that we've replaced. The other thing that's super important is we have to shuffle so that we can have random selection. So just like on our random assignment, random selection, if we're going to do something where we want it to be completely random, you can't just replace it, you have to replace it and shuffle it. Okay? So what does that look like? So you're going to pull a red card. So red cards would be 26 out of 52. And then you're going to pull a black card. So black card would also be 26 over 52, completely independent from those. All right, we replaced it, so my sample set stays 52. Now 26 over 52 is 1/2, So what I have here is 1/2 twice, which is 0.25. This becomes 1/4, which is 2/5, or which is 0.25. Okay? You spin the following spinner 5 times. What is the probability that you land on yellow all 5 times? So again, completely independent of each other. So probability that I have yellow, and this probability that I'm going to have yellow 5 times is going to be 3/8 5 times. Now, I don't know what that is, but if I plug this into my calculator, I would have 3/8 to the 5th power. So use your calculator on these, and this gives me 0.007, so not very likely, even though I've got 3 yellows on there. Okay? All right, let's keep going. All right, so those were independent events. Those don't affect each other, and now we're going to talk about dependent events. And so if you have a dependent event, events are dependent if they do influence each other. And most importantly, if they do influence your sample space. The occurrence of one event influences the occurrence of another event. So it's the same thing that we just said, okay? And this is usually trials without replacement. You pull one, you don't put it back in. Now, here's what this is. So this is saying the probability of A and B. So this is the general multiplication rule in a case where we have A and B are both dependent events. So this would say the probability of A, and then this would be written, so I'm going to write this down here on this line. This would be the probability of B given A has occurred. Probability of B given A has already occurred. And that's what this is. This is B given A. Now, we could take this and I could switch this up. And this says A and B. I could also write this as the probability of B times the probability of A given B has already occurred, right? So probability of B given A, because I'm looking for A and B, so either one of these are going to say the same thing, right? Probability of A times the probability of B given A, or the converse of that, probability of B times the probability of A given B has already occurred. So either one of these would satisfy this and statement right here. Okay, now what happens in this and statement, so now we have this symbol right here, and this would be the probability of A given B has occurred. We call that part of this the conditional probability. So up here it says conditional probability of an event is that one event will happen if it's known that another event has already happened. And we said that. A given B has already occurred. And so this is on your AP Stats formula sheet, right? But all this is it's our normal probability, general multiplication rule probability equation that's manipulated. So if I write my general equation, probability of, I'm going to say B and A is the probability of B times the probability of B given A. If I want just the conditional probability, so just this guy, then to isolate that, I would divide this by the probability of B and divide this by the probability of B. And I have my conditional probability statement, right? So in this case, whether I write this as A and B or B and A, I'm saying the same thing, B and A or A and B. That's saying that both of those occur. So let's look at this in terms of a Venn diagram, and then we'll get into some actual practice. So when you know something has happened, that changes the sample space. Specifically, it shrinks to the given event. If we know A has already occurred, so what I have down here, what I have down here is the probability of B. I'm going to write this. Probability of B given A has occurred. That's what this says in words. Well, I have to take care of this part first. Given A has already occurred. Well, given A has already occurred is this. A has already happened. So now, for B to occur, and that's what this says, if we know A has already occurred, that becomes your sample space. So this is my new sample space. So then for B to occur, it has to occur with A. Well, that only happens right here. So this overlapping region that we have right here is where B occurs given A has already occurred. Okay, so graphically, this is what we're looking for. But let's go look at some actual data here, pull some numbers into it so we can practice this. All right, so this first one, it says, I have a standard deck of 52 cards. What's the probability of pulling a spade and then pulling a 5? Sorry. Pulling a spade and then pulling a 5. So remember, I have to write my statement. So the probability, what I want is a spade and a 5. That's what I want. And what I have here is the probability of pulling a spade and then the probability of pulling a 5 given you've already pulled a spade. Spade is first and then a 5. Okay, so probability of pulling a spade, there's 13 spades in my deck of 52. Now I have not replaced that spade. I pulled it, it's out. So I have a new sample set. And that new sample set says I now have 51 cards. And then I'm going to pull a spade. Now it doesn't say, or sorry, then I'm going to pull a 5. It doesn't say a 5 of spades, it just says a 5. Well, I haven't pulled a 5 yet, so I still have 4 5s left in the deck. And if I multiply this across, I would have 13 times 4, and then I'm going to divide that by 52 times 51. Okay, so you see how I put this in the calculator, multiplied my numerators, divided by the product of my denominators, and I get 0.0196, or with this one, I would round this to 0.02, because I can't round that to 3 digits. Okay. Standard deck of 52 cards with the probability of pulling a jack and then another jack. So probability of pulling a jack and a jack, which is the probability of pulling a jack, and then probability of pulling a jack given a jack. So I know that there are 4 jacks in the deck of 52 cards. So now my sample space is 51 cards, but I already pulled a jack. So now my sample space only has 3 jacks left. So I started with 4, pulled one out, and then I pulled a third one, another one. So this would be 12 divided by 52 times 51, which is super, super rare, which we probably would have expected, 0.005. So very low probability of pulling 2 jacks back to back in a deck. Okay, so here's our sweet and salty table from last class, but we're going to mix it up a little bit. Okay, so we have this sweet and salty, same table that we had last time. So the question this time says, what is the probability you select someone who likes salty food and then select another person who likes salty food? Okay, so what I have, so probability of salty and, hold on, I don't want to do that, salty and salty. I didn't want to use an S because that could have been sweet. So probability that I pick somebody salty, and then the probability that I pick another salty given the first was salty. All right, so probability something salty. So yes to salty, that's this guy. So I would have 13 over 25. And I'm going to multiply that by salty given salty. Well, now my sample set's not 13 anymore. Now it's 12 because I've already picked one salty out, and this becomes 24. Okay, I'm going to save time and not put the math in. So what is the probability you select someone who does not like sweet food? So does not like sweet food, and then someone who likes sweet food. So here's what I have this time. So the probability, someone who does not like sweet food. So I'm going to say sweet complement, does not like sweet food, and someone who does like sweet food. So what does that look like? Probability of complement of sweet, so not sweet, times the probability that they do like sweet, given they don't like sweet. So what does this say here? What this is saying is that our sample space has changed, and we're only pulling out of the sample space here that does not like sweet food. All right? So if we look at that, the probability that they do not like sweet, so up here, this would be no sweet, probability that they don't like sweet is going to be 8 over 25. Now, the probability that they do like sweet, given that we've already picked someone who doesn't, is now going to be 17 over 24. Okay, so I don't know what that math is. We're not going to worry about it right now. Okay, all right. Now, these next two are very different. So let's talk about this. So if we look at one like this, what's the probability like you select someone who does not like sweet food and then select a person who does like sweet food? You're talking about two dependent events, two events here. Now, if we look at this one, it says, if we select a woman and find she has brown hair, that's an event, right? So probability of brown hair. What is the probability she will also have hazel eyes? Now, in this case, we're saying that this would be the probability that she has hazel eyes given she has brown hair. Let's look at this again. First, we select someone who has brown hair. What is the probability she will also have hazel eyes? This is different than what we have up here. We select someone and then we select someone else, right? But what we're finding here is our conditional probability. So what this is going to look like is it's going to look like this. I'm going to write this on paper just so I have more space. This is going to be probability that they have hazel eyes given that they have brown hair. That's what we're looking for. So what this becomes is the probability that they have hazel eyes and brown hair given the probability that they have brown hair. Now, if we go back to our notes and we have this part of our statement, right? Remember I said we could rewrite our statement. Well, this is what we're looking for. The probability that they have hazel eyes given they have brown hair. Okay? So what my formula looks like is the probability of hazel and brown over the probability of just brown. So, let me go back here to my notes. And here's what I have. So I want probability of hazel given they have brown hair. So where am I at on my graph where they have hazel and brown eyes? If I go up here, they have, brown hair. They have brown hair and hazel eyes. My numerator becomes 29. And what is the probability that they will have just brown hair? Well, just brown hair is going to be 143. Now, what I did is I pulled these from the chart. Now, I simplified this a little bit because what I did is I just picked the relative frequencies. But look what happens really. If I look at this, I would say 29 out of 313 people. And then I would say 143 out of 313 people. So what we know is that our denominators on this are going to cancel out, and we end up with just pulling these values directly from our frequency table. And if you don't know, don't know this, like you don't see this, if I write this just like old school division, and I have 29 over 313 divided by, because that's what this is saying, 143 over 313, and I do old school keep, change, flip, because I'm multiplying, I can cross reduce, so these go away, and I'm left with just those values from my frequency table. So what this turns out to be is 29 over 143, and that would be, I don't know, let's figure that out, 0.203. All right, let's look at this next one. If we select a woman and find she has brown eyes, what is the probability that she also has black hair? So probability that she has black hair given brown eyes. That's what we're looking for, okay? So if I write this out, I'm going to have the probability of black hair given brown eyes is going to be the probability of black hair and brown eyes divided by the probability of brown eyes. So I go back to my graph. So black hair and brown eyes. So black hair and brown eyes is 36 over the probability of just brown eyes. Just brown eyes is right here, so it's going to be 122. So 36 divided by 122 is 0.295. Okay. Oh, good part. Last part, showing independence. So if I'm going to show independence, so sometimes you're like, how do I know if these are dependent or independent? Because it matters, right? If it's independent, then we know we just multiply. If it's dependent, then we have a change in our sample space. So if we draw two cards with replacement, we know that this is going to be independent. We're going to put it back and we're going to draw again. If we draw two cards without replacement, we know that it's dependent. Okay? However, in the real world, sometimes it's difficult to determine if two events are independent or dependent. We do have a way to prove independence, either using one of these two formulas. All right? So, they are independent events if knowing whether or not one event has occurred does not change the probability that the other event will happen. In other words, the probability of events A and B would look like this. The probability of A given B is the same as the probability of A given B did not occur, right? Now, this would be the same thing with B given A. All right? So here is my probability statement. I think it's a little confusing until we just kind of work through it, so let's go do that. So it says we have this two-way table. How many packages are purchased based on whether it's fresh or frozen? Are blueberries and fresh independent? So what I have here is I'm going to say blueberries are A and fresh is B. And I'm just going to label those A and B so that we can use our formulas up here to make it make sense. Okay? So what I have is the probability of A and B equals the probability of A times the probability of B. Okay? Now, if I multiply this together, the probability of A and B. So this is saying that probability of A and B, so blueberries was my A and fresh is my B. So A and B together is going to be 20. If I pull this from the table, A and B, where do they both occur? They both occur right here. And that's 20 over 140. Now, if I have this, I want to multiply the probability of just A. So the probability of A is going to be just blueberries. So it's going to be 56 over 140 times the probability of B, which is freshness, and freshness is 50 over 140. All right, so let's look at this. So I'm going to plug this in the calculator. And what I have here is 20 divided by 140 is 0.143. Now on the other side, I'm going to have 56 times 50, that's my numerator, divided by 140 times 140. And I get 0.143. So, because of this, I'm going to say yes, they are independent. Now, if I look at my formula up here, and my formula says if I have the probability of B given A, then this is going to equal the probability of B. Okay, so let's test that. Let's just look at it another way. So if I have the probability of B given A, then this has to be equal to the probability of B. So if I look at the probability of B given A, so probability of B, sorry, move this up, probability of B given A. So the probability of B given A, so probability of B would be 20, given A, which is 56. So this is going to be 20 over 56. So given A is my sample set, so my sample set is 56, B is 20. So this is 20 over 56. And this has to equal the probability of just B. Well, the probability of just B is going to be this marginal, so it's going to be 50 over 140. So if I have that in my calculator, I would say 20 divided by 56, which is 0.357, and I have 50 divided by 140, which is also 0.357. So I can look at this strictly by plugging it into the independence formula, and I see that it works, right? This was just my normal is it independent formula. This is showing independence. This has to be true. And so based on this, we know we could have turned this around and we could have said probability of A given B is going to be the probability of A. And if I went in and calculated it, oh my goodness, sorry y'all. If I would have calculated it this way, I would have seen that I would also get the same results. Now, it doesn't matter that this is 0.143. What matters is that the left equals the right. And here what happens is the left equals the right. You'd have the same thing over here, the left equals the right. Okay, let's do another one. Let's do are avocados and frozen independent? Okay. Actually, I'm going to go ahead and pause it and let you try to do this one, and then I'll come back with the answer. All right, I worked this all three ways. Not sure which way you would do it. So here I said probability of avocado given frozen needs to equal the probability of an avocado. So here were my numbers. These numbers are not the same, so they are not independent. Now, look at this. Super important. 0.167 would round to 0.17, but they're not the same. This is why we don't want to round, okay? If I get over here and I did probability of frozen given avocado should equal probability of frozen, two numbers don't equal the same thing. And then if I just do independence formula, avocado times probability of frozen, again, those don't equal each other as well. However, look again, if you would have rounded this, they would have been the same. So don't round. But this is an example where no, they are not independent. I think that's it.